on a Thursday morning. This is a journey into the guts of GHC, into the core. So it's not sort of about the outsides, it's a bit about the insides. I'll try to explain a little bit about why you might want to know something about the insides. But it's very important to me that we have some kind of dialogue as we go along. If I just rant about GHC's insides, it won't be much fun for me, and it might not be much fun for you. So I'd really like it if you would stop me and ask questions and just clear things up as we go, because I shall probably say, at least it's hard for me to pitch this. I don't quite know how much everybody knows and how much they don't. So if you have a thing you think, I wonder what Simon meant by that, then stick your hand up and ask, because the chances are that 2/3 of the other people in the room have got the same question, but they don't dare ask. Okay, so please do that. That would help me. All right. So here we go. GHC's version of Haskell is what Microsoft calls a rich language. What does that mean? It means it's a large, complicated, ad hoc, rather ill-defined language with a very long user manual. There's almost nobody who knows exactly what it is. This accurately characterizes Microsoft products, and I think it probably accurately characterizes GHC these days. Even I have trouble understanding everything about what's going on. So how do you kind of stay, not only that, but the compiler itself has accreted a lot. It's quite a big and old compiler. This figure, I think is from our paper about the about GHC, which is about 5 or 6 years ago that Simon and I wrote. So these figures are out of date, but it still gives you an idea. That's right. These figures come from 2011, so this would be bigger now, right? So these are lines of code back in 1992. 28,000 lines of code. In 2011, there was 140,000 lines of code, and I'm sure it's more. I think it's still quite small, considering all the things that it does. The runtime system hasn't grown quite so much, but it's still a pretty big beast, right? This is, read Simon Marlowe hacking lots of C code down here. So there's a big, old, 25-year-old code base to work with, right? And a big, complicated language that people keep adding more features to. So the question is, how do you stay sane in the midst of all this kind of ad hoc complexity? And that's what I want to give you a handle on today. The primary way in which we kind of try to stay sane in GHC land is this. We take this enormous language, which does actually have a representation as an algebraic data type. So if for those of you who looked inside GHC's source code, this is the hsyn directory, right? And it's a data type with dozens of data types and literally hundreds of data constructors. So it pretty accurately represents the source language syntax. It's type checked, or it's parsed, renamed, type checked, and then desugared into a very small language. And that's what I'm going to talk about today. So this is the intermediate language that then is used in the rest of GHC. So it's and the idea is that all of this, that to a large extent, you don't need to understand the details of all of this part. For lots of purposes, you can just understand this guy. If we can squeeze a new feature here into the same language here, then we have some reason to believe that we haven't added anything fundamental. We've merely added, as it were, syntactic sugar. Make sense? As a sort of organizing principle. Yes, Mark. Yeah.
That implies the type check happens only over the full source language?
It does.
Another intermediary?
No, the type checking happens on the source language, in its full glory.
What?
Yes. So that means the type checker has many, many cases, because the source language has many, many cases. But it also means that type error messages come out saying something about the source language, which is really very important. And there's a whole other story about how to stay sane in the type checker that's to do with separating constraint generation from constraint solving. But that's another talk. So very good question, thanks. Yeah, Jeremy.
You said something about almost confident that you add nothing to the language if it compiles into core.
Oh.
Can you
So core is more expressive than the source language, as you'll see. There are definitely programs we can write here that we cannot write here. This is because there's some deficiencies here. With explicit type applications and so forth, we could get there so it's close but not there. But it's a good criterion. But at the moment, no, it is. This is super expressive, this little core language, as you'll see. Okay? So it's worth contrasting a bit what happens over here in the source with what happens in the core language in ways other than simply the size. So here's the top line is size, right? But so this left-hand column is the source language Haskell. This is the internal core language, right? So the source language is very big in terms of number of cases. The source language is also implicitly typed, right? So we have lots of type inference going on. In the intermediate language, it's explicitly typed, so there's no type inference, right? So as we'll see, it's very explicitly typed. There's no guessing about what types are in core. You look at a Haskell program and you think you have to mentally reconstruct types sometimes, not in core. Typically, one example of that is that binders typically just come like lambda. When you say lambda x, I should have written arrow here. You just write lambda x. In core, every binder comes with a type annotation. That's one example of what I mean by saying it's explicitly typed. So because the source language is implicitly typed, there's a type inference algorithm, which is complicated, quite slow, and a bit, it's ad hoc. There's lots of choices that you make in designing a type inference algorithm. Say this work and this won't work, and they're design choices that you might make to say what seems convenient for the programmer. In the intermediate language, there's no type inference. It's only type checking. It's very simple. It's very fast. Right, so by the same token, when I said there's lots of choices here, specifying exactly which programs will pass the type checker is quite complicated, right? Programming language designers do a lot of work on this kind of thing. They try to say, specify precisely which programs will pass a type inference engine. For core, it's very simple to say which programs are type correct. No, again, there's no argument here. And also, to make type inference go through, you have to make some ad hoc restrictions, like let's see, monomorphic recursion, right? When you have a recursive function with no type annotations, you can only call itself at the same type as it starts. That's called a monomorphic recursion. If you want polymorphic recursion, you have to add a type signature. That's an example of a kind of ad hoc restriction that makes type inference feasible, but there are no such restrictions in core because it's explicitly typed. You get I'm just trying to give you an intuitive feel for the kind of trade-off. Very explicit, but very principled, very simple, okay? All right. So why is it a good idea to have a typed? I've been stressing a lot about types here, right? That all of this stuff is about types. Why have a typed intermediate language at all? I mean, after all, virtually no other compiler in the world does, in a thoroughgoing way. The front end's types, and often you get into an untyped intermediate language that they beat on. Why? So let's see. This first thing is actually is nothing to do with types. The first point is just saying a small intermediate language is good because it means that optimizations only have a small language to deal with. So that's fairly obvious. Why typed? Well, there are two reasons. So one is that some transformations or optimizations or code generation steps can make use of types. That's a sort of modest thing. You could probably just about get away without it. Another very powerful one, though, is that we can type check the intermediate program. So we make lots and lots of transformations on the program, and at each stage we can run this thing called lint or core lint, which is a type checker for the core program. Now, if the compiler is all correct, you haven't made any mistakes in writing the compiler, lint will always say, very good, right? Correct or type correct Haskell program yields type correct core program, transforms the type correct core program. So lint would always say things are good. But what happens if you make a mistake when you're writing the compiler? Without lint, what do you get? Well, you make some error early in some early optimization. It dribbles down through the entire compiler. It goes into the code generator. It generates code. You run the code. You get a seg fault. Now what? You have to backtrack up that long chain to find the original error. And that's very, very painful, right? The seg fault is far away from the problem. The problem, the sort of runtime problem, the runtime problem is far away from the original error in the optimizer, right? But with lint, it says, after pass 3, type error. What a great way to find. I can't tell you how many years of my life this has saved. So I would be older than I am if it was not true. So this is, in a way, is a security check for GHC itself. But the other thing is more principled, which is that the design of core itself has given us a way to reason about type system extensions. It's kind of what I said earlier. If you can add a new feature to the source language, and it adds nothing to the core language, then it's kind of like just syntactic sugar. But there are some features that we've added to the source language, like type families or GADTs, which have required changes to the intermediate language, and making the right change, the smallest change that achieves as much as possible with a small principled difference, rather than something that exactly mirrors the source language. That's the trick. You get the idea? So it sort of forces you into a principled way of thinking, what's the smallest thing you can do? Okay? Oh, and when I say sound here, what do I mean? Well, supposing I add some feature to my source language. Let's say I don't have a typed intermediate language. I add some feature to the source language. I write a bit of type checking code that alleges that it checks that it's type correct, and it goes through. Very good. Compile, 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 segfault. What could go wrong? What could be wrong? It could be the type checker for the source language, right? The type checker for the source language could be allowing through some program that it shouldn't allow through. And for new features, that's rather likely, right? In a complicated language like Haskell. So in a way, the core lint is not just a checker for optimizers, it's a checker for the original type inference algorithm, which, as I've been discussing, is itself pretty gigantic. Make sense? So, okay, so I want to say why I think this is all a very significant feature of GHC, and indeed, one that I don't really know any other production compiler that does this in this remorseless way, right? That is statically typed all the way from the front end to the code generator. Mostly they're statically typed at the front, and then they sort of throw up their hands and go untyped effectively. All right? Yeah.
You mentioned runtime error.
Yeah.
Segfault.
Yeah.
Are we saying that there is no segfault in Haskell because we have this type check?
Yes, yes. So is there no segfault? So I claim that if lint, right, if this pass says, no matter what the early optimizations have done, they might have changed 1 plus 2 into 1 times 2, which would be a semantic error, but it's not a segfault error. So, but if lint, so lint won't complain about that, but if lint says it's fine, then there should be no segfault. Now, of course, you might have unsafe coerces, and lint just trusts you when you do that. You might be calling C functions, and they can segfault, but provided you're in pure Haskell, the idea is, yes, if lint says right at the end of the pipeline, lint says it's okay, it should be okay, yeah. So it's a sort of end-to-end check, as it were. Was there somebody else who had something to ask? Yeah.
Is there any check that the types from the search language to the core mean the same?
Is there any check that the types in the source language match the types in core? So actually there is, yes. So the data type declarations in the source language effectively are mirrored so as data type declarations in core. They're the very same types. Okay, so I'm going to give you, so I just want to finish this preamble by saying, why should you care about this at all? So I think the main reason you should care about it is because it's really very interesting, right? It's kind of cool when you, I hope that you'll like it, but actually it's also useful, right? So it's useful in two ways. It's a sort of high leverage piece of knowledge, right? So it's not a very big language, as you'll see, but it's pervasive in GHC. So as soon as you want to take the lid off GHC at all, it's going to be useful to you. And why might you want to take the lid off GHC? Number one reason is performance debugging. Your program isn't running as fast as you wanted it. You run the profiler and it says something, that some function is at fault and you wonder why, right? You're going to end up looking at core before too long. Somebody's going to say you should do that, and you should. So it's a powerful lever on understanding the operational stuff, because Haskell is very high level, right? Core is much closer to the operational behavior. And you might even want to write a core-to-core plugin. This optimization pipeline I described allows you to plug in new core-to-core passes of your own. So that's quite fun to do. So if you know core, you can do that. And you don't need to know anything about the source language and its myriad complexities. You only need to know about core to write a core-to-core plugin. So it's a sort of high point of leverage. All right? Okay, so that's the end of the sort of scene setting. So I'm going to sort of dive in to tell you a bit about what core is actually like. All right? So what do we want? Well, clearly we want the lambda calculus. Right, I'm sure you have all read Guy Steele and Jerry Sussman's papers, Lambda the ultimate go-to, Lambda the ultimate procedural, Lambda the ultimate assignment, whatever. There was a whole series of papers from MIT. They're great reading. You should go back and read them if you haven't. So we know that Lambda is essentially, you can do anything with Lambda. But we do need a typed Lambda calculus, right, because of all this stuff that I've been describing. So my initial idea back in, I suppose, about 1987 or 8 was to start with the Lambda calculus and just sort of sprinkle some type annotations over it. But then the question was, how should we sprinkle them to make it typed? But they don't want to be buried in type annotations, and also types might change as we optimize. So I just want to give you the concrete example of that, because that was the first major insight that I got in this, so I thought I'd share it with you. Here's compose, right? This is the type of compose written in Haskell. It takes two functions, f and g, and we compose them to make a function from A to C. Okay, it's written dot in Haskell. Now, let's see. So here's the code for compose. So I've written lambdas. I'm hoping that you know about backslash lambda in Haskell. I'll often write it with the Greek lambda symbol here. Here it is decorate. So this is a sort of core-like language. I'm really writing in core at this point. So lambda f, lambda g, lambda x. Then I'm going to apply g to x and apply f to that. All right? I'm going to call the intermediate tump. What type does tump have? Well, kind of it has type B, right? Whatever g returns. But what is this B? Right? It's sort of, who binds B? It looks like a variable, but there's no binding site for it. There's an occurrence of f here and a binding site for f, but there's no binding site for B. That's already a bit suspicious. But it's even worse when you transform. So supposing I have a call of compose to is, pos, and neg. So neg takes an int to int, and is, pos takes an int to bool. If I compose them, I should get an int to bool. Well then, so now if I simply inline compose, there's its definition again. Inlining just means replacing the call with a copy of the body, making suitable substitutions. So I'll substitute for f, I'll substitute is, pos. For g, I'll substitute neg. So that gives me this. Right? And I just copied the body, this let temp. But what's this let temp equals b? Let temp of type b? That doesn't look right. What type is temp? Rob, what type is temp?
I don't know.
Ah, yes you do. Look, neg applied to x. What type is neg? Int to int.
Okay.
So it's going to be an int. Yes, very good. So this b, jolly well ought to be int. But I couldn't get that just by copying this right-hand side. Do you see the problem? There's something fishy here, something not working right about types. So what do? Well, the amazing thing is you don't have to invent anything. You simply have to go to the computer science library and pull off the shelf, papers by Girard and Reynolds, who are extremely clever French and American computer scientists who invented all this stuff. It's called System F. So their idea was, well, look, they kind of independently invented this at the same time. Just bind the type variables too. So in the original definition of compose, just as for this arrow here, I get a lambda, but for this arrow, I get this lambda. For this arrow, I get this lambda. For this arrow, I get this lambda. So for this for all, I get these lambdas. So that's this upside down thing is a big lambda, and it binds A, B, and C, which are type variables. So now this is good because B is now bound here, right, has a binding site. So whenever you have a lambda, you're going to have an application when you call it. So when I call compose, I better apply it to something. What should I apply it to? What are A, B, and C? They are type variables, so when I apply them, I should apply them to types. Of course. Right, so, welcome, Mr. Girard. Right, yes, so compose, the call to compose now looks like this. Right, instead of just applying it to is, pos, and neg, I have to apply it to 1, 2, 3 types. The type to substitute for A, the type to substitute for B, and the type to substitute for C. What could be simpler? So this is the definition of compose now. This is the call of compose, and when I inline it, I do exactly what I did before. I copy the body, replacing the lambda-bound variables with their, the arguments. So instead of A, I replace int. Instead of B, I replace int. C, replace bool. F, replace is, pos, neg. So I just got 5 things that I substitute. Does that make sense? Exactly the same as what I did with the ordinary lambdas, but for type lambdas. It's so cool. And then you get out this tump with the right type int. So the whole thing's stable under beta reduction, which is just what we want because the compiler does a lot of beta reduction when it's optimizing programs. Okay? Oh, this was amazing. I was scared about this at first because what's all this business about passing types to functions? Can you do that? It seems like a very strange thing to do. But after you do it for a while, it begins to seem natural. I thought it was very odd to begin with, and now I think how could every child of 3 should do this. It's just the most natural thing in the world. So do try to get used to type application and type abstraction. It's very, very pervasive stuff, certainly in core. Okay? Now, so that's the key idea behind System F. So System F is actually only the lambda calculus together with big lambda and type application. For core in GHC, we needed to add a bit more, right? Algebraic data type, so this is part of core. So standard algebraic type data type, so as well as being source language constructor, also a core language constructor in effect. Data constructors, so they can appear in terms, like, so this is a perfectly good core term where just is the data constructor for maybe. We're going to need case expressions to take them apart. This is what pattern matching turns into. So case X of nothing goes to there's a case expression, and we're going to add let expressions as well. Okay? And that's pretty much it. This was core. The first instance of core was exactly this. And the amazing thing is that Girard and Reynolds told us exactly where to add type abstraction and application, and it just worked. It was a direct conversion of theory into practice. I was so pleased about this. Phil Wadler told me how to do this, and this was 1989 or something like that. Okay, so far so good? Any questions at this point? So we need to do a little bit more, because then we started saying, oh, the source language is now doing a bit more that is going to need something from the target language. So here's the first thing. So at this point I'll say that I'm going to explain various things which, if you don't get them 100%, you will still get something for the rest of the talk. But I do want to put some things on the table. But please still ask questions. This is the first one. So this is an existential. So here's a data type declaration, and here I've written it in GADT format. But it's not a GADT. The return type here is just A, right? So I could also have written it in that old-fashioned existential format. So here, what type does T1, the data constructor, have? For all A and B, takes a B and a B to A and gives a TA. So what's weird about this is that the B here doesn't appear in the result. So you should think of it as a pair of a value and a function that takes that value and returns an A, and that all gives me a TA. So I can use this this data type with lots of, so long as this type and this function, sorry, this value and this function match, different T1 calls can use different Bs, right? But they could all be T of ints. So you'll have seen this, I think, in Haskell source programs. But what does this say about the internal language? Well, when I pattern match on T, when we're here, I should have said, oh, look, I should have said here, every binder is explicitly annotated, so I should have put x:int here or something. Every binder is annotated in core. So when I do, so here's F, let's say it takes a TA to an A. What does it do? It's just going to apply, it's going to pattern match on the Y, that corresponds to this, and the G, that corresponds to this function, and it applies the G to the Y, which should work because this function takes an argument of type B, and it's got a value of type B to be applied to. Okay? That should be fine. But now what happens? What is this B? So I was ranting before about how I want my type variables to have a binding site. What is the binding site for B? Well, it's not bound outside by some big lambda. It's bound by the data constructor itself in the pattern match. So here in the pattern match, as well as matching, binding the variables Y and G, I also bind a type variable, B. And this colon star means of kind star, of kind type. Does that make sense? So that means that pattern matching on X here brings B into scope in the whole body, and incidentally, B is then used in the types of other binders in the same match. Yeah, Mark.
That induce kinds into the core?
No, so the colon star, the kinds bit is a sort of orthogonal question, right?
Okay.
So.
You got that there because it doesn't seem like the star seems like a very different thing than big lambda A.
Yes, it is. So for the moment, forget about the star.
All right.
Just imagine that I bound, rather like in here, I didn't put any kinds, right? Yeah. But probably in this slide, I shouldn't have. Right. So this is just the first thing to know, that just as the ways that you can bind type variables, you can bind them with big lambda, and you can bind them in pattern matching as well. Just like term variables, you can bind with little lambda and with pattern matching. Okay? All right, so that's existentials. But now let me return to Mark's point and just mention kinds and kind polymorphism. So in Haskell, even Haskell 98 had these higher kinds. So B could, in fact, have had kind star arrow star, right? And when I said that every bound variable in core is typed right? I said I should have put a type on X here. Every binder is typed. This is a binder, so it should be typed. For a type variable, that means it should be kinded, right? So in fact, I do have to stick a kind on every variable, including for the big lambdas. So back here, I should have put kinds on those as well, okay? In the real thing. So, and this might be star, it might be star arrow star, or with kind polymorphism, so this is a relatively more recent addition, but just slips right in, so I thought I'd put it in here. In a kind polymorphic data constructor or situation, we may have kind variables as well. So here's muct, and its declaration in source Haskell is f of a arrow t f a. So there's no existentials here. I'm just using this to illustrate kind polymorphism. So what type has muct got? Well, this f here, what kind does it have? And a, what kind does it have? What clues do we get from this? Only that f of a, since it's an argument to an arrow, it must have kind star, right? It must be a type. But f, what does that have to be? It just has to be compatible with a, right? So f here could have an argument of type k, provided a had kind k, right? Then that makes f and a compatible, right? Then f applied to a is compatible and gives a result of kind star, which is good for arrow, all right? Yes? Aren't I missing something? Oh, yes, sorry, this is a bug. Right, this should say TFA at the top. Thanks. Yeah, sorry about that. Yeah. So let's see. So here is the type of muct that is now kind polymorphic. It will work for for k being a star, or k being star over star, any old k. And the kind of t itself, the data constructor t, its kind is, for all k, it takes a k to star, that's this guy, and a k, that's this guy, and gives a type, because TFA is a type. All right? But that means that if you think about it, let's see, let me just look at what this source term turns into. So here's a source language term, muct of just x. By the time it gets to the core, remember I've got to make those type applications explicit. But in this case, there's three for alls here. There's 1, 2, 3 type arguments. Well, not quite. There's one kind argument and 2 type arguments. So here is muct applied to the one. I'm using an @ sign here. I'm being a bit inconsistent about this. I'm using an @ sign to indicate a kind or type argument, and no @ sign to indicate a value argument. So here are the 1, 2, 3 type or kind arguments. The first one says how to instantiate k. The second one says how to instantiate f. And the third one says how to instantiate a. So I'm trying to, in some ways it doesn't matter if the exact details of this pass you by. I just want to give you the idea that there's this sort of simple story that we're very explicit about binders, and every time we have a for all in the type of something, we have some kind of argument in a call of that something that says how to instantiate the for all. Just as every time we have an arrow in the type of something, we have a value argument in its call sites. Okay? So the nice thing about this is, though the kind polymorphism made a rather late appearance in GHC, it was only about 5 years ago, it just slipped right in. There's no, we didn't really have to add anything new to core. We did have to add a bit new to core to get existentials, because we had to have these binders here. Okay? So that's it for the sort of first part. If you can get to this point with the lambda calculus, with data types, case expressions, let expressions, and the only scary bit is these big lambdas, and which can work over kinds as well as types, then you're in good shape to understand core. Yeah.
What does it say, data TA, not data TFA?
It should say data TFA. Yeah, I had that question. No, this is just a bug. It should say TFA. Sorry about that. Maybe I should actually. I'll just move to the next slide, and then you won't be seeing it anymore. But I'll try to fix the slides before I hand them over to Andres. That is confusing. Yes. Data T. Oh, yes. So of course, I didn't mention here that really T, since it's polykinded, right? Every call of T Just as every call of muck_t in a term must be applied to kinds that instantiate its kind fools, so every call of t in a type, like here's a type, must be applied to the kinds that instantiate its kind fools. So that's why I had to say here t applied to k. So this is a sort of core language type, if you like. So really, t does take, well, as you can see, it takes, as it were, two types and a kind as its arguments. But we don't write that explicitly in the source language. That's a design choice, exactly how you notate it. But in GHC, you write TFA. But if you had some kind of explicit kind application, you could maybe, in the source language, you could maybe imagine writing data t at k or something. Yeah. OK? Yeah, at the back.
So there are some kinds of parameters that are implicit, like the net parameters.
There are some kind of variables that are implicit.
Parameters that are implicit.
Some parameters that are implicit, yes.
Like the at k over there.
Yes, this guy is implicit, yeah.
But function calls also have them if they're polymorphic.
Yes, so here's a function call to muck_t.
So my question
Right.
is, how happy are you with the fact that they are so implicit?
Oh, how happy am I that so much is implicit?
Right.
Well, how would you like to write, instead of writing this, would you like to write this in your Haskell program?
I agree. The other side of the story is sometimes they don't match up and you get a type error.
Yes, that's right. So perhaps sometimes you would actually like to write the thing at the bottom. Just to be explicit is rather like writing type signatures, right? You like to say, don't give me grief. I want to be, there's a lot going on behind the scenes, and I'd like to make it explicit to, as it were, document the way my program is working. Good idea. This is what, so for a long time, we've thought Haskell should have some kind of visible type application. That is, the ability to do this explicitly in the source language. And in fact, Richard Eisenberg is at this very moment, in a branch of GHC, has this going. So you will shortly be able to do this. I think even with the @ sign is the notation he's using for it. So good idea. And that, going back to Jeremy's question, is the main thing that will allow you to essentially take any core program and reflect it back into the source language. Yeah. Is it a compiler hint? Well, no, it's still source Haskell. When we write this in source Haskell, it will be the source language, and it will say, then there'll be a type system that says, well, if you have an @ sign, then the thing on the left should be something that has type for all, something that you can instantiate. So no, it's not like I'm switching language. It's just the source language will support explicit type application just as the internal language does. Only it's a bit more complicated in the source language because we want to say sometimes you have explicit type application and sometimes not. You can choose. Whereas in the intermediate language, it's compulsory. So there's a design choice about exactly how you do that.
So,
Yeah.
will explicit type applications in the source language give you impredicativity?
Yes, once we have visible type application, right, that is explicit type applications in the source language, then you could put a for all type here, and that will give you impredicative polymorphism for those who are not afraid of long words.
And that will be allowed again.
That will be allowed again, yes. But of course, it'll be rather inconvenient to use, right? But you'll be able to do it, right? At the moment, you just can't do it. Yes, so it'll be allowed again. Yes, it was sort of allowed at one point, but then disallowed. Yeah.
Could you go back one slide?
Yeah.
So here in the data constructor, we kind of, or when we apply T1, we kind of lose the information.
Yes.
Which cannot be true because.
Good questions. This relates to when you call the constructor for the value arguments, you imagine that I'm going to at runtime I allocate an object in the heap that contains the value, right? The arguments of the constructor. When I pattern match on it, well, I can get those arguments out. And your question is here that when I construct a T1, there's this heap B thing that's sort of hidden. Is it stored somehow, right? So that when you pattern match on it, you can get it out. Well, operationally, no. That is, at runtime, no. Because remember, all of the stuff that I'm showing you is completely compile time stuff. By the time it gets to the code generator, all types are erased, and these B's here have gone away, right? So the actual fields, the bits in the heap allocated data structure don't have any bits for B. They only have bits for Y and for G, right? But while the optimizer is optimizing, absolutely it does capture the B type inside T1. So inside the optimizer, as it were, it looks like T1 applied. In fact, it looks exactly like a call to T1. Do I have a call to T1 anywhere? I do not have a call to T1. So it'll be T1 applied to int, and then some function, and then some function. So at runtime, no, is the short answer. Yeah?
But that only works because you have a uniform representation of all values. I mean, if it's sometimes were 32 bits or sometimes 64 bits, you
Yes.
have to know at runtime.
Yes, that's true. Type erasure is because all values are represented by, all boxed values at any rate, are represented by 32 or 64-bit pointers. That's quite true. And if they weren't, then you could record type representations explicitly and look at them at runtime, or you could generate different versions of the code. There are lots of ways of doing that. But GHC's never done that. Very good, very good. We're getting into the guts. Anybody else? So one of the side messages here is that when I said core is closer to the machine, it's not like, x86 machine code, but you can look at core and give it an operational reading. A let does allocation. A case does evaluation followed by pattern, single level pattern matching. I should have said case is only a single level pattern match in core. So that core has a very direct operational reading, which is helpful in doing performance debugging and in reasoning about space and time as well. Yeah? Can you see allocation? Yes, it's called let. I'm being a bit sloppy here. So function application like here, here's mkt. There's an allocation here as well. I could have said let v equal just x in mkt blah, blah, blah v, right? Then it would have been even more explicit. But you can pretty much see allocation in core. It's let and arguments, non-leaf arguments. There's no way to see any other allocation.
So if I see anything else, I should not think that is allocation.
If you see anything else, yeah, I'll try that for the first approximation. Yeah, like if you see a case expression, no allocation. What else might you see? Well, constructor application. Yes, if you see a tail call, like if you see case blah 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 of nothing arrow g of x, then that g of x is not allocated. It's just a call to g. So yeah, pretty much let and function arguments are what allocate. Okay, let's see. So to be here is then. I just want to sort of step back and say what have we seen so far? So this is core: variables, constants, that is literals, value application and value lambda, type application and type lambda. This is e tau. That's this at stuff I've written. But here I'm writing e applied. Maybe I should have said at tau here. Let expressions, case expressions. What are lets? They have bindings, which are pretty simple. They're either non-recursive, a typed binder equals the right-hand side, or a recursive group with a bunch of typed binders equal to their own right-hand side. What is case? It's a bunch of alternatives, and each alternative looks either like a constructor applied to variables, no nested patterns, just a data constructor applied to variables, or there's a default alternative that allows you to do a catch-all. And this is it. That's the whole intermediate language, right? So you can go home now. You understand core, right? It's incredibly small. Here it is. This is the data type taken from the compiler. This isn't some sort of some version that I've simplified for expository purposes. I got this from the source code of the compiler. This is the 25 years later. This is what it looks like. Expressions of variables, literals, applications, lambdas. Oh, so something funny is here. I'll come back to that. Let expressions, case expressions, and I'll come back to these types. Now, let's just look at this lambda and type. So over here, I had two sorts of application and two sorts of lambda. But over here, I have one sort of application and one sort of lambda. How did I do that? Well, it's because the lambda binds a variable, and the variable says whether it's a term-level variable, an ID, or a type-level variable. This is actually type or kind, right? So a term-level variable is a name together with its type. Remember, all the types are, every lambda has its type annotation. That colon tau, that's this part here on the binder. And every type variable has its kind. That's there. Now, let's see. And types are kinds. So types and kinds are collapsed in the representational sense. You can still think of them as being stratified, but they're represented by the same data type. So this is just a type synonym. It's not, in the implementation, it's not kept separate. what else to say here? Oh, what about type application? So here I had E applied to a type, not E applied to a term. So you might have expected to see tie-app of expr and type. But instead of doing that, we just do an app of type T. So this constructor here embeds types as terms, but really that's only used as the argument of an app. It just turned out to be much, much more convenient to slice the cake this way around. Looks as if it's a bit too flexible, but it's much more convenient. I've tried it both ways. This is much better. Okay? Yeah?
Has it always been like that kinds are equal to types? Because we recently had the merge of unifying kinds and types.
There are really two different things, kinds and types, but they're represented in the compiler the same way. So in the source language, and indeed in core, kinds and types are sort of stratified into separate levels. Now Richard and Stephanie and so forth are indeed working on making types and kinds be the same, in every respect. In which case, this will become a sort of true synonym rather than a kind of engineering compromise. So that's still to come, but it will, and then there'll be collapse. Yes?
In what order can I apply type arguments?
Can you apply type arguments?
Let's say I'm partially applying a function.
Yeah.
The second argument is polymorphic, but
Very good. So in what order can you supply them? It's driven by the type. So just as you say, if I have a function of type a to b to int, you must apply it to an a and then to a b. Okay? So when you have a function of type for all k, f of kind of k to start an a, you must apply it first to a k, and then to an f that has that kind, and then to an a that has that kind. So it's driven by the order of the for alls, just as the value arguments are driven by the order of the lambdas, the arrows.
But so what if my first argument I want to partially apply?
If you want to partially apply it, you can indeed stop after any of these. You could say mukt applied to star.
Yeah, but then let's say I have a to b to something.
Yep.
I apply the type for a.
Yep.
I want to apply to the value instead of now applying.
No. So if you partially apply mukt to one argument, right, here, you just apply it to star, then you get something whose kind is for all f and for all a, right? So you must then apply it to the f and the a. You can't start applying it to the value arguments then. In other words, even when partial application, you've got to keep to the same order. It's exactly the same story as with term-level partial application. No different. Yeah, Mark.
When you added the type arguments from the source language, like in the first example before this, you added 3 arguments. What order did you choose to add them in?
Oh, you mean when I, why did I go lambda ABC? Very good, yes. So this is a choice that the type checker makes, right, when converting from source language to intermediate language, right? So when we get visible type application, right, so if you wanted to call compose with explicit arguments, now we have to have a story about which order we abstract them in, right? And that is probably the most awkward or corner in the design of the source language feature visible type application. Yeah. But while it's completely invisible, we can just say, don't ask, we're going to do something.
Right. Because you always apply,
Because we're generating all those applications.
they're always all applied before anything happens.
Yeah, that's right. Yeah.
In your abstract syntax for the core language, where do things like casts go?
I haven't got to cast yet. I hope I'm going to get there, but that, 9:42, yes. But we are going to get to cast shortly. So I haven't quite finished this. I just wanted to, this is, as it were, we're now up to about 1995 or so.
You said this is all. But you said
Oh, all right. There's going to be 2 more constructors. Yeah.
So with regard to actually making the type applications visible, presumably that's very complicated because when you have polymorphism, you want to make sure you can use things in the right place so the type arguments get passed in the right order.
So visible type application is complicated when you have polymorphism. Well, of course, visible application is all about polymorphism. But you only need to apply a function to a type if it's a polymorphic function. And you do have to apply them in the right order. So, yes. You should read the paper. Right. So, Richard Eisenberg and Stephanie Wywick have this paper on their homepage called Visible Type Application.
I don't mean about the source, the Haskell source.
Oh, in core?
I mean in core.
Yes.
When you actually synthesize the type application.
Yes.
And you're doing it automatically.
Yes.
If you get any of them in the wrong order, it doesn't match.
Oh, that's right, yeah. So when the type engine, the type checker, synthesizes the type applications, right, these guys, when it synthesizes these guys on the way from source to core, it had better do it right. You're right, it had better. And lint will check that it does. So indeed, type inference, therefore, is more than just a matter of checking that the source program is type correct. It actually generates a translated program which does have all these explicit type abstractions and applications in it. And that's then desugared into core. Okay. Parche, Andres, I think it's still pretty impressive, even at 1995, that this compiler, that it's a very old compiler that still has a very, very small intermediate language, and it's due to these guys, right? You should give them the credit. I think it's really quite remarkable. I want to mention one other thing, briefly in passing about it, which is a difference from what Girard and Reynolds did, is that you'll notice that here, variables here, which can occur in terms, concentrate on IDs for the moment, those are the term level variables, they come with their type. So what that means is that every occurrence of a variable is already decorated with its type. So if I was writing this in a more abstract syntax, as well as writing lambda x colon tau, I might write x colon tau here as well. So the leaves, the occurrences of variables, have their types as well. That's easy to do in an implementation, because they all just point us to the same thing. Right? It would be very tiresome to do if you're writing it out textually. But what that means is that if you want to say, what type does an expression have? So this relates to the lint thing, right? What type does an expression have? What is the type of V? Well, just take the type from in here. That's easy. That's what var type does, incidentally. It takes an ID and gives you its type. What type does a lambda have? That's easy too. Take the type of the bound variable and make an arrow to this. You have to do a bit more with for-alls, which I haven't done here, but it's pretty simple. So essentially, the expr type function it's a pure function, no environments, no monads, nothing. Just takes an expression and gives you its type. So it's like and it's very, very useful internally in the compiler. It's completely pure. Okay. I'm going to skip this. And I think I've sort of said everything about this so far. So now I want to just give you a little bit of a feel for what it feels like to sort of actually do the sort of core diving stuff when you're using GHC. So here's GHC's pipeline, which I mentioned earlier. We parse, rename, type check, desugar. Now we're into core. So from here, this part here is all core stuff. But there's a loop here, meaning I do a lot of transformations. And here are the transformations. There's specializing overloading, floating out, floating in, demand analysis, cardinality analysis, CPR analysis, arity analysis, call pattern specialization. All of these are core-to-core passes. And then there's the mother of all core-to-core passes, which is called the mighty simplifier. And it kind of does lots of simple local. Think of it as a sort of super peephole optimizer for core. Right? So these guys do sort of global heavyweight things. They're the big intelligent guys. And the simplifier just sort of does little local optimizations to get rid of these guys are free to generate stuff that isn't really, in the best form. And the simplifier then tidies it all up. The biggest thing that it does, though, is inlining, replacing calls by their bodies, and applying rewrite rules. Those are both very important. And then it does a ton of other things, beta reduction and so forth. Okay, so that's the sort of overall pipeline. Then once we're finished with doing all of that, we then feed it into the code generator, essentially. So the main payload of this talk is in this middle bit here. Okay, so that's the sort of framework. Now then, what might you actually encounter if you were kind of trying to peer into core when you were using GHC? So here's a little Haskell program. It just has a single function that adds 1 to its argument. So if I say, GHC-c food, and then I say dedump simple, that says, show me the optimized core. That is what comes out here after this little pipeline is run. Then what does it show me? Well, so it shows me a bit about the size. Then it says, here's the type of f. And now it says, foo.f is lambda x APE, has type ghc.types.int. And then it's an application of this thing plus, there's a type application to int and to this funny thing, ghc.num.$fnumint. And then there's the x. And here's the 1. Doesn't look much like 1, does it? This 1 looked like 1. This looks like I hash of 1. That's because it's a, this is the fact that boxed integers in the source language are represented by an application of the iHash constructor to the unboxed one. So that's an unboxed data type in there. Okay? So the reason this APE thing is because internally we've done lots of renaming. There might be lots of X's, so we need to give them a unique names to keep them apart. What's this? This is the num dictionary. This is without optimization. So I've done no optimization, so this will work, but it's not very efficient, right? Because it's still using the record of methods for num. So if I want to optimize, what do I get? So here is what I get if I add -o and then show me the optimized core. Look at the bottom here. Now this looks a bit better. Lambda x, case x of, oh, let's see, mumble, 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 mumble. Oh, I'm unpacking it to get an x1. So this guy has type int hash. So I get, that's the unboxed int. Now I add 1 to that unboxed int, and then I package it up with iHash. So I'm unboxing it, adding 1, and boxing it up again. Okay? So you sort of see the moving parts happening here. This awk business is to do with occurrence analysis. It says the bound variable of the case is not used. I'm not gonna, what's all this stuff? This stuff is extra information that's attached onto the identifier by some of the analyses. So arity says it's got 1 argument. Well, I'm not going to ignore no calves. Strictness, and this demand type, this says, what does it say? Oh, it says I'm strict and I use my argument exactly once, and the M says it has the CPI property. I'm not going to go into all of this, but if you're interested in strictness analysis, this is the place to look. Unf, that's the unfolding, and I've had to strip off some of it. This is to do with what would happen if I tried to inline this at some other call site. So I don't want you to understand all this. I just want to get you the sense that you could understand it if you wanted to dig in. Let's see. Here's what happens if you, if you show the output of the whole pipeline. If you say, instead of showing the outline, you just say dshow passes, it'll show you the passes that are taking place. So here's the parser, the renamer, the desugarer, simplifier, tidy, and core prep. So you see, without -o, there's not a lot going on. No analyses of any kind. But when I add -o, I get a lot more passes. And so this means you can see them all taking place. And if you then want to see the details after each pass, you can add some more flags. I'll tell you about it in a sec. So somebody had a question at the back? No, maybe not. Yeah, Mark.
Why do we show simple and not tidy? Tidy said it had nice names.
So this is...
Everyone always says do dedump simple. And I just like
that is, in fact, the output of the tidy phase. Look, look here it is. Right?
Oh, I see.
So
Even though it says simple, it's
yeah, that's right. It is. So what actually happens is that after all the simplification, there's a kind of make everything have nice names. So I just wanted to... there's quite a lot of flags that will give you control over how much you can see if you want to look into this stuff. Here are some of them. So I don't expect you to remember this. I just want you to get an idea of what flags are available. You can look them all up in the manual. So these first ones, ddump parsed rn tc ds, these are the ones that let you see the output of after the parser, after the renamer, after the type checker, after the desugarer. Right? So that's all the front end. Then there's decore lint. That runs lint after each pass. It's not run by default. You have to switch it on. But if ever you have a problem with GHC, the very first thing you should do is to switch lint on, right? Because that often nails the problem much earlier than it shows up. You know, you've got some unexplained behavior, switch lint on. Verbose core-to-core, I use this quite a lot. It's just like dshow passes, like this one, but in addition, it spits out the entire core program after each pass. So I almost always redirect that to a file, because it's a bit long, right? But it's kind of useful to see it going by. Then you can get yet more information. Ddump inlinings says, oh, simplify. Every time you're thinking about inlining something, tell me whether you did or not, and why. Ddump rule firings and rule rewrites says, oh, simplify. Every time you apply a rule, tell me. And rule rewrites gives you more information than rule firings. It's a sort of more verbose version of the same thing. Ddump occurrenal says, so the simplifier works in a two-stage process. It first of all walks over the entire program doing occurrence analysis, that is, finding out, attaching to the binding site of a variable information about how often it occurs, and then it does a simplified pass. So it goes occurrence analysis, simplify, occurrence analysis, simplify. Ddump occurrenal shows you the results of the occurrence analysis, which can be very helpful, I find. Then there's some flags for adding more verbosity or switching it off. dppr debug prints kind of yet more information about everything, right? So you want to hold your breath if you do this, but if something confusing is going on and you think, I don't know what's happening there, I switch on DPPR debug just to see a bit more stuff. These ones are to do with suppressing stuff, so core can be a bit overwhelming. Even this was perhaps a bit more than you might want. Imagine it replicated thousands of times. So you can suppress a whole bunch of things. The module prefixes, like here, it's printing ghc.types.int. Don't give me this stuff, just tell me int. Right, so sometimes you want to see which int, but mostly you just like, give me a break, int. Right, so module prefixes, uniques, don't print out that x_APE, that's too much clutter, right? So you would switch a lot of these things off. Okay, so I think that's it for sort of a quick how-to for how to get a picture of what's going on when you're running GHC if you want to look at core. Okay, any questions about that? What I'm going to do before we finish is just give you a quick run at coercions. In the next 5 minutes. Darn. Oh, rats. I knew this would happen. Okay. So, yeah.
So, going back from our perspective, as just a user,
yeah.
in my software, my module, and getting compiler error.
Down to make compiler error more reasonable. I don't know what compiler error is.
So,
do you mean a type error?
Type error, sorry.
Oh, type error. Okay. So it's all in the type checker. By the time we get to what we're talking about today, all done.
It's all done.
All done. Yeah. Okay. After the type checker, there should be no more type errors.
I see.
If lint complains, it's a bug in the compiler.
Okay.
Yeah. So there's no attention given to nice user errors in all of this stuff. Yeah. Okay. So I'm going to put the slides for this talk on the I'm going to give them to Andres, but I'm going to do sort of essentially 3 minutes on how coercions work, because I just want to give you a little window into that. I thought there probably would not be time to do so. I much prefer to spend the time, having fun together, right, and actually talking to each other than just ranting. So, but nevertheless, I'm going to spend 3 minutes ranting. So, here is, because it's a very interesting problem. Here's a GADT now, right? Here's T-bool as a result. Look at this case expression, right? So what does it do? It says this function takes a TA and an A and gives a bool. If I match on T1, right, then I know that A is in fact bool, right? So that means that this Y guy, I can say not Y in my source program, can't I? Right? Because in the T1 branch, look, in the T1 branch, I know that this A is bool, so that A must be bool, so that Y is a bool, so I can say not of it, okay? But something looks very wrong here in core, because Y has type A. So why am I notting it? So one way to address this might be to say, let's make core lint, clever and know about GADTs and stuff. Bad idea. One reason it's a bad idea is here's another problem, right? I might imagine picking this binding up. This binding doesn't mention Z, so I could pick this let binding up and float it outside the case, like this. There's no lexical clue that says that's not right, but of course now this really is wrong. Right? Because now I'm not inside the branch, so why isn't it int? So this caused me sleepless nights when we were introducing GADTs. I thought, what are we going to do to make this work? So here's the idea in one slide. What we're going to do is we're going to say, when we match on T1, we bind a variable, this C guy, that you should think of as giving me evidence that A and bool are the same type. Okay? So it's kind of like a proof witness. It says, trust me, A and B are the same type, and you can utter this spell to prove it, right? So you bind the spell, and then you use the spell down here, right? So instead of just Y remember has type A, but I need something of type bool. So I say Y cast by C, and C is this A equals bool spell, and the rule is that if E has type tau, and C has type tau twiddle sigma, then E cast by C is type sigma, right? So I use the spell to convert the A into a bool. And that simultaneously solves both of these problems at once. It solves the first problem because now Y cast by C has type bool, as it should, to be an argument of not. And it solves the second problem because I can't pick up this binding and float it outside the case, as I did here, because it mentioned C, right? So it solves both the things at one blow. So this is a very simple and beautiful idea, and it goes very, very far. So GHC consistently uses these things. They're called coercions. It binds them in pattern matches. You can also bind them in lambdas. So they're a new sort of variable. And then there's this cast form. So I didn't really have to add much to the intermediate language. The cast is the main thing. In fact, here is the change to the intermediate language to respond to Andreas's question. We got to add cast, which takes an expression and a coercion. Just as we have types embedded in the term language for type applications, so we have coercions embedded for coercion applications, and we do need a whole new data type for coercions. Okay, that is a significant addition. But that's the most significant addition. Oh, and in variables, as well as term variables and type and kind variables, we also have coercion variables. And that's it. Turns out to be very simple, nice addition to the language. And there's quite a lot more about this in the slides that I'm just not going to have time to talk about here. Skip. I want to sort of wrap up. Really, just to leave that, you can read this as the last slide while we take questions. Yeah.
When you build up these coercions,
yeah.
I think the type checker for GHC does I suppose does smart things to come up with the right coercion.
Yeah.
Is there also the sugar in there? Like, is there no is the composition of these coercions and all of these things is it done explicitly in core? And
yes. How can we compose coercions? Good question. Well, I should have paid you to ask this question. So here, I've just got y cast by c, but I might need something. Let's see. Yes, here's an example. Supposing I want to take a g. This is a new function g, which takes a ta to a maybe a. And how does it work? Well, it pattern matches on t1, which has a bool inside it, and it returns just z. So z is a bool. So now z is a bool, but I want a. So I need to take this coercion, which is an a equals bool magic spell, and turn it into a bool equals a magic spell. So I do that with sim, and then there's a whole little family of coercion composers, right, which you don't see at all in the source language, but when the type inference engine is busy applying type functions and dealing with GADTs, it's going crazy building these coercions, right? And when you print core, you will see big coercions lying around. That's why we have de-suppressed coercions, right? Because they can become dominant if you're not careful. So yes, the type inference engine, in addition to adding type applications and kind applications, is also adding coercion applications and the coercions themselves.
Will we have access to this language with explicit applications?
Oh, will you have access to coercions? No, I don't think you will. No, we haven't gone as far as visible coercion application, and I'm not sure we should. But that's an interesting thought. Okay, go. Yes, design a feature. Start a wiki page. Yeah. Anybody else? Yeah.
So you built core for Haskell, but do you think at some point other language will start targeting that?
Oh, I built core for Haskell. Will other languages start targeting it? I don't know whether other languages will target core. Let's see. Two ways to say this. I think that other statically typed functional languages that are lazy might well target core directly, and then they could use GHC as a back end. That's entirely possible. I think probably the ideas are likely to be more durable than the actual implementation. Yeah.
You mentioned laziness. Does that appear in core?
Oh, core. So when we talk about laziness, yeah. So this let, it's a lazy let, and the optimizer assumes that it's lazy. Now, it would be much nicer to say, here's a core language that will support both strict evaluation and lazy evaluation, and you sort of desugar a lazy language one way and a strict language the other way, but the optimizer neither knows nor cares. And core is not far from that. So Max Bollenbroek and I wrote a paper called Types Are Calling Conventions, which is the nearest thing I've ever got to an intermediate language that really properly does support both strict and lazy evaluation, but we've never retrofitted that to core. That would be a nice thing to do, at least have a try with. Yeah.
Does case mean strictness here?
Yes, case definitely means strictness. So let, you should think, mean lazy. Case means evaluate this guy, right? And pattern match on it, yes. So case is eval. Case is a combination of eval and pattern matching, and that's a little bit unsatisfactory. You'd really like them to be separate, one eval construct and one pattern matching construct. And types with calling conventions makes that possible, the language described there. Okay, well, I think you could have some fun by looking at some of this. And I think it's what's nice about this is that it's a very direct example of taking scary type theory stuff and putting it actually into practice in a compiler that all of you use. And I think to me that's quite an exciting intellectual adventure. And this business about using that I spent so little time on, I think that's the main sort of intellectual progress we've made on core is this part, and it's gone very far as well. It's a single idea that's covered multiple source language features, so I'm pleased about that, and I would encourage you to dig into it and have a look. Thanks very much for listening. I'm going to be around all day, and I shall be wandering lonely as a cloud, so do come and talk to me. But I'm not going to be here tomorrow. Great.